yeah, so this talk is about the problem of counting BPS states with a framework that we call exponential networks, and everything I'm going to tell you about is the fruit of joint work with Sebastian Panergre and Mauricio Romo, and it's based on 2 papers from a couple of years ago last year, plus a paper that should appear soon. So the plan for this talk will be to start with an introduction to the kind of problem we want to solve, the mathematical and physical aspects of the problem. I will then give you a very rough sketch of what exponential networks are. And then I will flash a few applications and results that we can obtain with this technique. So let me start by clarifying what I mean by BPS counting. In fact, so this is the problem of counting BPS states, and you can view it from different angles. It connects to several topics. For example, if you're familiar with quantum field theory, for you BPS states could be related to the study of non-perturbative field configurations, such as instantons, monopoles, vortices, or kings. And a bit more precisely, you're not so much interested into just solving, say, the self-quadratic equations, but you're interested in properties of the moduli spaces of solutions, things like the cohomology. On the other hand, if you're a string theorist, then BPS states, of course, show up in the guise of D-frames, maybe boundary condition for open strings, but also as worship instances. So they connect to the subject of topological strings. And finally, BPS states also show up in math, actually in quite a few contexts. But perhaps the one that most directly relates to what I'm going to talk about is the subject of enumerative geometry. So this is the study of questions such as counting mass from Riemann surfaces into certain manifolds, or studying moduli spaces of special Lagrangians of certain, say, Claviaus. So all these are different ways to think about BPS states. I'm going to actually make use of all of these perspectives later on. And conversely, everything that we're going to learn will actually have something to say about each of these. So now let me specialize to a specific setup that we're going to study in the rest of this talk. I'm going to consider M theory on a background which is R4 crosses 1 times X, and I'm going to choose X to be a Clavia threefold. And for this talk, I'm going to assume it's a toric threefold. This could be relaxed in principle, but we're just going to stick to that. Then, in this background, the BPS states that we're interested in can be engineered with M2 branes wrapping compact 2 cycle, C2 times R, or M5 branes wrapping R crosses 1 times a compact 4 cycle. Now, there's an alternative viewpoint on this setup, which comes through quantum field theory. In fact, this M theory background can be described in a certain limit by 5-dimensional gauge theory. It's a supersymmetric gauge theory with minimal supersymmetry, whose field content, couplings, and masses are determined by the geometry and topology of X. So I'll call it T of X. And the BPS states that arise from M2 and M5 branes translate into the quantum field theory as electric particles with a mass, roughly speaking, determined by the volume of the compact 2 cycles, or magnetic strings in the case of M5 branes with a tension determined by the volume of the 4 cycle. So the goal then is to study this problem, and what we want to do is we want to develop a framework that allows you systematically to compute the spectrum BPS states. So what does that mean? It means that for any type of electric particle or magnetic string, or maybe a bound state of those, we want to compute a certain invariant quantity known as the BPS index and denoted by omega that contains some information. You can roughly think of it as the dimension of the Hilbert space for particles or strings with a certain charge. And from now on, I'm going to actually switch from M2 and M5 branes to a different way of labeling charges. So if you're familiar with that, fine. If you're not familiar, it doesn't matter so much. But sometimes I'm going to refer to D6, D4, D2, and D0 branes.
Sorry.
Yes.
So this omega of gamma, is it an index of some operator?
It's a secondary super trace. So yes. Okay. So before I get into the details, let me also give you a rough idea of the kind of results that we're going to see later. So the kind of things we can compute with this technique are, for example, the BPS index for an arbitrary number of D0 branes. And we're going to see that this always corresponds to minus the equator characteristic of X, well, suitably defined because X is on the path. On the other hand, if X does not have any compact 4 cycles, so you have a toric threefold with, say, only compact 2 cycles, then we can compute the BPS index for D2 branes wrapping the compact 2 cycle bound to an arbitrary number of D0s, and we can check that this coincides with genus 0 or above invariance. So that's a nice check. We can also consider toric threefolds with compact 4 cycles, and in that case, we can compute BPS indices of D4, D2, D0 bound states. And what we find then, in the examples we study, is that the BPS index recovers the buffer weakness invariance associated with C4. So the first 3 bullet points are the things we can actually compute directly. But then if we leverage some other techniques, for example, Vol-Cross and formula, we can also compute, we can also include D6 branes, and therefore compute a higher rank numerical bounds and bounds invariance. All right, so let's get started with the main subject of the talk. So what are exponential networks? So exponential networks are actually a very young invention. They're just a few years old. There's just a few papers on the subject, but it turns out that they rest on 2 main ideas. And the first idea is actually quite old. It goes back to a 1960 paper of Klebner, Mayer, and Warner. And the idea is that if you're interested in the BPS states that they just described on toric threefold X, you can approach the problem from the mirror side. So there's another Cabiao, Y, which is a hypersurface in C2 times C star squared, and it's described by this equation UV equal to a Laurent polynomial in X and Y. And one of the ideas of this paper is that then the BPS states that you want to study actually map to geodesics, which I'll describe in a moment, on the Riemann surface sigma, also called the mirror curve, which is defined by setting F equal to 0. So how does that work? So sigma is defined by f of xy, Laurent polynomial equal to 0. So it's defined as a complex curve inside C star cross C star. You can think of it as a Riemann surface with some handles and some punctures. And BPS states are defined by, well, as geodesics, which means cycles on sigma, or embeddings of S1 into sigma, subject to a constraint. So there's a differential, lambda, which you can, well, it's defined on C star and C star, but you can pull it back to sigma. And what defines this geodesic is the requirement that along the geodesic, the phase of lambda is constant and equal to an auxiliary phase theta. So that's it's the geometric version of the BPS condition. Now that's nice, but it's still pretty hard to work on generic Riemann surfaces in practice.
Sorry, what does it mean in phase? Right now, lambda is one form. Do you integrate it?
Well, yeah, okay. I'll be much more precise about that later. But what you do in practice is you take this geodesic, you take a tangent vector to the geodesic, and then you contract it with a one form that gives you a complex number. I'm talking about the phase of that complex number. Yeah, but yeah, later there will be an equation for that. Okay, so that's already simplification of the problem, right? We don't have to worry anymore about 4 cycles and 2 cycles in X. we just need to study some geodesics on a Riemann surface. But working on a Riemann surface is not yet so simple because this could be arbitrarily high genus. So what people do instead is they say, okay, so this is defined in C star cross C star. So what we could do is we could choose a projection, for example, to the x-plane. And then what we can do is we can study the projection of this geodesic. It's going to be a cell connection connecting, say, two branch points. Okay, that's the simplest example of a BPS state. Now, that's a way to think about the BPS states that comes out of this 96 paper, and it still doesn't answer an important point about our question, which is how do you now use this picture to compute omega? How do you extract quantitative information about BPS states? So to do that, we're going to take advantage of a phenomenon observed in quantum field theory by Gaberdiel. And what we're going to do is we're going to take the setup that I described previously in M theory or its quantum field theory counterpart, and we're going to enrich that by introducing a new object, namely an M5 ring. So we're going to choose a Lagrangian submanifold L. This is a Lagrangian inside X, it's non-compact. And we're going to place an M5 ring on L times R2 cross S1. And on the quantum field theory side, what this does is it generates a new quantum field theory. This is going to be a three-dimensional theory leading on R2 cross S1. And again, the structure of this theory will be determined by the properties of L. Now, once you introduce this object, you also introduce a new sector in the Hilbert space of BPS states. And what this looks like from the viewpoint of quantum field theory, well, first of all, there will be the BPS states of the 3D theory itself. So there's a 3D BPS spectrum. And then there's also a mixed sector of bound states of 3D and 5D states. So how does that help to compute omega, the BPS index of 5D BPS states? So the main point is that you should think of this three-dimensional theory as a tool, a probe, that allows you to study the five-dimensional theory. Because it turns out that through interactions between 3D and 5D BPS states, there's a lot of information about omega of 5D states that is contained in the spectrum of three-dimensional states. But the point is that it's a lot easier to study 3D states directly. So that is indeed the purpose of exponential networks. So what they do is they essentially compute 3D BPS states and they extract information about the five-dimensional spectrum that we're ultimately interested in. Okay, so now what are exponential networks in practice? So an exponential network is a web of trajectories on the x-plane, the plane of the projection. And the shape of this network is determined by the geometry of the covering surface and by an auxiliary phase theta. And the shape of these trajectories is determined by this equation here. So tau is the proper time along the trajectory. Yi and yj are two roots of the equation f of xy. So you choose two sheets of the covering. And n is some integer. So this equation is a differential equation. You can integrate it, you determine the shape of a trajectory. But then in addition to this geometric data, which was formulated in this way in a paper of Igers, Amani, and Johannes Walker, in addition to that, there's also some extra information attached to each of these trajectories. And this corresponds to the spectrum of 3D BPS states. And it turns out that, well, one can show that this is determined by the topology of the network. So this is a very long story. I'm not going to get into the details, but feel free to ask if you're interested. And that's, so this combinatorial data attached to trajectories is what we worked on. So there are some basic building blocks in an exponential network. First of all trajectories are solutions to that differential equation, and the boundary condition are the branch points. So you integrate starting from branch points. Then, as they evolve, there may be some intersections, and what happens at the intersections actually depends on the data associated to each trajectory. So there could be, say, one new trajectory that's born, or infinitely many new trajectories. And then, so given these rules, you can build your network. You take the explain, you evolve your trajectories, build a whole network. So what do you do to compute the BTS index of 5-dimensional states? So to do that, you have to start varying the values of theta. So theta appears in the differential equation, which means that as you vary the phase, the shapes of trajectories will start to change. And for special values of the phase, what happens is that the topology of the network degenerates. You could have, for example, two anti-parallel lines. And when that happens, you have a saddle connection on the base that is actually the shadow of a cycle up on sigma, which is your BTS state. And then the claim is that now with the information attached to these trajectories, you can actually compute omega directly from the topology of this saddle. So just to recap the approach that exponential networks give you for computing BTS states is first you choose a model. So you fix a choice of Gaberdiel X, a choice of Lagrangian manifold, and that identifies for you a mirror curve f of x, y equals 0. Given that curve, you can use it to define exponential networks. So you plot your network for various values of the phase, and then you look for those values for which there is a saddle connection that appears, and then you apply our rules to compute omega for each of these saddles. So that's the full BTS spectrum of M2 and M5 range that I talked about at the beginning.
So this should be independent of the choice of L? Or?
Great question. It should be independent. So it's a subtle point. L indeed determines the three-dimensional theory, so the exponential network itself, so sigma will depend on L. Also, so therefore the exponential network and the data in the network will depend on L. However, for any choice you make, you get all these different Riemann surfaces. And at the end of the day, when you go and compute the five-dimensional spectrum, all of these should give you exactly the same result.
But that's not manifest on the way you.
Not at all. Yeah. Not at all.
But you probably checked it in
the
example.
That's right. Thanks. Very good question. Okay, so let's go through some examples. So the first the first example is the simplest possible. It's C3. And okay, so you may wonder, it doesn't have any complex cycles or four cycles. How interesting can it be? So the mirror curve of C3 can be chosen to be of this form. There is a choice of framing, which needs to be quadratic, but it doesn't matter. You can take higher framing if you wish. So this Riemann surface has two sheets, y plus and y minus, and there's a single branch point on the explain. So what you do is you identify the branch point, you start evolving your trajectories, and then you start plotting your net. And if you do this for several values of theta, this is what you find. So on the top left is theta equals 0, evolving all the way to theta equals pi. And as you can see, there's some intersections and some new trajectories being generated. But now if you want to study 5D BTS states, you have to look for saddle connections. And well, you have to train your eye a little bit perhaps, but the saddle connections that you see on this slide are just at the beginning and at the end. Those are the only ones. So you focus on those, and so this is what happens at theta equals 0. In this picture, there's actually not one saddle connection, but an infinite tower. So there's a black trajectory that starts from the branch point from above. It goes around the puncture, self-intersects, and goes back into the puncture, into the branch point. And this is the trajectory whose cycle has homology class gamma. And then everybody else, the blue trajectories, there's an infinite tower of them. They're born from the self-intersection of the black one. And it turns out that their homology cycles are actually multiples of gamma, integral multiples. You can also compute the mass of these BTS states, and you find that they're multiples of 2 pi over r. And so if you're familiar with string theory, you recognize this as the max of a D0 ring. And then finally, you can apply our rules to compute the BPS index for all these BPS states, and you find that omega is -1 for all of them. So this is the spectrum of the zero branes on C3.
So what corresponds to K here?
Oh, K, well, you mean in the picture. So this is K equals 1. The black trajectory is K equals 1. But then the blue trajectory is, well, so there's an infinite tower of them. They get closer and closer to the limiting red trajectory. Each of them is higher K.
I see, so that you wind around more and more.
Well, yeah, that's right. Actually, it's a bit more subtle. So if you follow, say, the inner blue line, it goes around, then the innermost goes around, and it goes through the self-intersection, it becomes the outermost. And then it goes once again in, and it goes back to being the innermost. So each of these blue actually goes around only twice. But the differential that you use to compute the period of this cycle gets a logarithmic shift. There was this logarithmic shift in the equation for the spectral curve, and that's why you get this different. Yeah. So it's not just about winding; it's also about how you shift the differential. Okay, so that was C3. Let's move on to something a bit more interesting, namely the result conical. So now we have a compact 2 cycle. There will be some new BPS states. This is the mirror curve. It depends on a modulus Q, which I'm going to fix to be real valid and greater than 1. So this curve has 2 branch points. Again, we plot the network starting from there, and we look at various phases. So let's start from theta equals 0. The kind of picture you find is this one, and it should look familiar. So these are just 2 copies of what we saw before for C3. And so each of them is a tower of these zero branes. Once again, you can check your homology classes and periods. And well, the BPS index, as you may guess, is now -1 plus -1 -2. So that's the expected spectrum. But then you can look at other phases, and you find saddles, for example, at theta equal pi/2. So this is a very simple saddle connecting the 2 branch points. If you remember, I set Q to be a real and positive. So this BPS state actually corresponds to a D2 brane. So its mass, one can compute it, is 1/r log Q, and the BPS index is 1 for the single lift of this, and 0 for all multiple lifts. That's a correct spectrum of D2 branes. And then you can go on. You can look, for example, at the phase of D2 D0 bound states, or D2 with 2 D0, and D2 with any number of D0s, and you always find 1. So you find an infinite tower of 2 D0 bound states, and that's, of course, to be expected. These are KKMOs on a single M2 brane from the viewpoint of M2. Okay, so the last example is the most interesting one. It's a local Hirschberg surface, F0. Now, this is very interesting because it has a compact 4 cycle. And if you're familiar with these kind of problems, you may know that this makes the story a lot more complicated, but also a lot more interesting. So here's the mirror curve. It has 2 moduli. And now the new feature is that the spectrum will depend on the choice of moduli. Here's wall crossing. So I'm going to fix the moduli to something that resembles the conical point. So QB is -1, QF is 1. And if you plot the network, there's 4 branch points. And you have to plot at different phases. So for example, at theta equals 0, what we see is 3 simple saddles. One can study their D0, D2, D4 brain charges. They turn out to be these complicated combinations for the 2 red saddles. And then the black one is a simple D4. They all have omega equal 1, so very easy. And at theta equal pi/2, we also have 2 BPS states, the red and black, with these combination of D2 and D4 charges. But then things in this model are actually quite complicated. So as soon as you start varying the phase, you see a lot of saddles. So for example, here you see this black one that's supported by these 2 branch points, and then there's an inner one, and this would have omega equal -2. This would have omega equal 1, and so on. So there's many. The spectrum is actually very rich. There's an infinite number of BPS states. Some of them can be listed systematically, so they come in families. But in fact, most of them are actually so-called wild BPS states. They have omega of absolute value greater than 2, and it's very hard to give a systematic description, at least at this point in modular space. Right, so I guess my time is nearly over, so let me wrap up. So I hope I convinced you that the framework of exponential networks produces some rather concrete and explicit results for a whole range of toric labial threefolds. It's fully systematic. It comes with a bit of a price because computations turn out to be a little bit hard at times. And so what I talked about today is the main purpose, which is computing BPS states, but there's several further applications that would be interesting. In particular, in the 4-dimensional limit, when you take the radius to 0, 5D theory goes back to Sumner-Whitten theory, broadly speaking. And exponential networks become something that is known as spectral networks. And spectral networks play a role. They, for example, they come up as Stokes graphs in the context of exact WKB analysis, and they also allow you to construct coordinates on Kitchen systems. So one may ask whether there's extensions to these applications to find radius. There's some concrete reasons to think that the answer should be yes for both of them. Another interesting connection is to BPS quivers. This was the main motivation for Eagers, Manning, and Welker. And also it would be really interesting to include D6 branes directly into the picture. This is something we haven't been able to do yet. And finally, it would be interesting to explore more choices of the Lagrangian. So, for example, in the result conical, you could choose a non-polynomial, and therefore you would be studying exponential networks for augmentation polynomials, augmentation curves of knots. Okay, so I think I'll stop here.
Thank you. Any questions or comments?
So for exponential networks, from the point of view of the first point under the further applications, in terms of say exact WTB analysis, do you expect to recover maybe some kind of WTB analysis for difference equations? Or
that's right. Yeah. Again, this is an expectation. So there was a really nice paper I think a couple of weeks ago by Kashaev and Gaberdiel about researches for difference equations. I was not aware of any previous rigorous. I mean, of course, people study difference equations quite a lot, right. I think this should be connected to that. So the difference equation would be the quantization, roughly speaking, of the mirror curve, which, when you take the limit r goes to 0, goes back to the Schrödinger equation, whose WQB analysis is connected to spectrum.
So if I understand you correctly, as you vary theta, you're going to see a different part of the BPS spectrum. So you have to go to different values of theta to really explore the entire.
That is correct.
Is it clear that you'll see the entire BPS spectrum as you vary all values of theta? Or
right.
Would it be
It should be clear. So it's clear from the interpretation of theta. Theta is the phase of the central charge of a BPS state. So since phases can only be between 0 and 2 pi, as long as you scan carefully, you shouldn't be able to see all of them. I mean, you can ask a question like,
yeah. So then you can calculate omega, but do you know which BPS state you calculated the charge of, or is that sort of something you then have to sort of interpret?
Right, very good question. So when you work with these networks, you're on the mirror side, right? You're working on the mirror curve, and you may say, okay, I'm studying special Lagrangians on the mirror, help me out. But then how do you go back to X, and how do you map it to D2, D4, D0 central charge? So it's a little bit of an art. So there's several ways you can do it. So there's some mathematical results that give you a map between, say, exceptional collections of coherent sheaves on X and special Lagrangians in Y. So there's results from the math literature. A bit more concretely, you could play some games. For example, in P1 cross P1, what you could do is you could take a decoupling limit. You could take a limit in which one of the P1s grows infinite size, and then you recover geometry that is C3 mod Z2, and there you know who's a D2 brane and who's a D0 brane. It's very easy. because central charges are actually just directly determined by the model. It never happens. Doesn't receive any non-trivial fractions. In general, it's hard. This is a very good question.
Perhaps I would propose to postpone questions to the coffee break. So thanks again.